Okay, so now we are Calc 1, Day 13, Chapter 4, Section 4, and we are going to take a look at indefinite integrals and the net change theorem. So, what we looked at in Section 4.3, we're going to use today as well, but now we're looking at indefinite integrals, so we are saying that we're going to take f of x and integrate it, and we will have our big F of x. Now, what this means is that if I differentiate my large F of x, I will then get my F of x. So, the one thing that we have to remember that is included in this, when we have an indefinite integral, we're going to be adding our constant because we don't have boundaries here, so we're going to have to add some sort of constant to make up for that value when we integrate, that we might have a c of x or c. Okay, so let's take a look at a couple real quick easy examples to refresh what we were taking a look at before when we do the antiderivatives. If I have the integral of x squared dx, that would be x cubed over 3 plus c. Okay, and if I then took the derivative of this, when I differentiate this, I will in fact get x squared. Alright, so let's look at a couple other real quick review examples. Let's say I have secant squared x dx. And if I integrate my secant squared, I have to be thinking in my mind, what would I differentiate to get secant squared? And that would in fact be my tangent x plus, again, c. And again, if I differentiated tangent x, I will get secant squared x. So that's how you can check yourself. Once you integrate, you can go back and differentiate to see if they are in fact inverses of each other. Now, there's a table on 322. Just like we had when we did our derivatives, we now have a table for integrals, table of indefinite integrals. So the first one says that if I have some kind of constant here times my function, I can integrate and then multiply by the constant. So we'll say that maybe this is 1 million or 100. I can just factor it out per se, put it in front, integrate it, and then when I'm done, I can multiply it through. If I have a constant k, so k is a constant, and I integrate it, that will be kx, which will be plus c also, because I still might have a constant here that when I differentiate it, I get 0. The next one, again, looking at reviewing your trig functions, they put them in here for your ease of referring. So if I have sine of x dx, that's going to be negative cosine x plus c. Secant squared x is tangent x plus c. Secant tangent is secant x plus c. Cosine of x is sine x plus c. Cosecant squared x is negative cotangent x plus c. Cosecant cotangent x is negative cosecant x plus c. So there are your trig integrals. Over here, we're taking a look at if I'm adding or if I'm subtracting even. If I'm adding or subtracting, I can integrate my first function, integrate my second function separately. Here we have our power rule for integrals, so our reverse power rule from what we did before. we're going to add 1 to our exponent over that n plus 1, and then of course plus c. So one of the things we looked at the very end of the last section was if we were integrating 1 over x squared on a closed interval of, I think it was 0 to 3. Let's flip back and take a look. Yep. Okay, so it was under 0 to 3. Well, the question was, what's the problem with this? Here it is. What's wrong with this calculation from -1 to 3? From -1 to 3. Well, we have to take a look at what that graph would look like if I have 1 over x squared. And let's see if it's in back of our, well, we have 1 over x here, so we can use that as our guide for 1 over x. We can see that it is not defined here at 0. So the problem with our last example that we looked at is it wanted to know what this value was from -1 to 3. Well, we can't have the value from -1 to 3 because it isn't continuous. So if it isn't continuous, then something's wrong. So you have to make sure that it's continuous on the integral that you're integrating. So if I have this here, we need to understand that this interval is bigger than 0 to infinity, or from -infinity to 0. And that is going to be our guide. As long as we recognize that, then we can say that we can integrate this and in fact get -1 over x plus c, as long as x is smaller than 0 or x is bigger than 0, because that is where it is continuous. Okay, let's go to example 1. Example 1, we have, and I'm on page 322 if you're following in the book. If I have my, let's see, my integral of 10x to the 4th minus 2 secant squared x, and this is in parentheses because I'm integrating the whole thing. And remember, these two together are a symbol, okay? This just tells us with respect to what we are integrating by, so the variable. Now, I can, by using the laws that I just looked at, break this apart, and I could say I have 10 and then integrate x to the 4th minus, and then also 2, integrate secant squared x, and I can break it down like that. Now, of course, I have to put dx in here. I'm terrible at my notation sometimes when I'm going through and solving problems. So, okay, so here we go. Here I'm going to use my power rule, and I have x to the 5th over 5, and this is times 10, minus, and then 2, and if I integrate secant squared, I will get tangent x, and then of course I have to say plus c. So when I reduce this, I will have 2x to the 5th minus 2 tangent x plus c. And that's my answer. Okay? All right, so that's example 1. Let's take a look at example 2. Example 2 says evaluate cosine of theta over sine squared of theta, and this is d theta. So now if I want to take a look at breaking this apart, what do I have here? Because you might have to use your identities when you're integrating to have it make sense. So if I take a look at this one, I see that I have a cosine over sine here, which is a cotangent, and my 1 over sine then would be cosecant. So I'm going to take this as cosecant theta cotangent theta, and again d theta. So the reason that I'm doing that is I know that cosecant theta, cotangent theta is negative cosecant. So I have now negative cosecant theta plus c. So in this one, I had to manipulate, use my identities to change this around to make it in some kind of form that I recognize, and then go to my table of indefinite integrals and see, oh, my cosecant x, cotangent x is negative cosecant x. So that is why I changed it to that form so that I could do that. All right? Okay, so example 3. Here we have, looks like we have a definite integral here. And I'm going to take a look at that from x cubed minus 6x. And this is all with respect to x. So first thing I need to make sure of is it continuous on this bound? And it is, in fact, it is a polynomial, so it is continuous at all reals. So now when I integrate, I will have x to the 4th over 4 minus 6x squared over 2 plus c. And if I simplify that, this is what I get. Okay? So here I'm, not plus c. Well, why not plus c? Because I have boundaries. I'm stuck on doing indefinites. Okay. Now let's plug this in. And 3 to the 4th is 81. So I'm going to have 1/4 times 81 minus 3 times 9, which is 27. And I'm going to subtract from that my zeros, so it's going to be 0, 0. So that's gone. Okay. So now I have 81/4 minus 27. And if I put that in my calculator, I'll get negative 6.75. Now you should recognize this because we took a look at this example in 4.2, compare it with a calculation in 4.2. Let's go back and look at it. Let me find that example. So when we took the integral here and we used our method of finding our rectangles before, our first shot we had negative 3.9375 when we took a look at 6 rectangles. Then when we did it as the limit as it approaches infinity, we then did get negative 6.75. So you can see how accurate we are now just by integrating and using our power rule of also getting the answer negative 6.75 and a much easier process. Okay, example 4. Example 4 is from 0 to 12. And I have x minus 12 sine of x dx. All right, and if I take a look at integrating that, I will have x squared over 2 minus, now here I have my sine of x, so if I integrate this, I will get 12 negative cosine of x. Okay, 12 negative cosine of x. And I am looking at this from, it says 13, 0 to 13. Oh no, 0 to 12. I have my glasses on right now. There's the problem. 0 to 12. Okay. So let's take a look at what we have here. We're going to have 1/2 12 squared minus, no, plus, right? Plus 12 cosine of 12. Okay. So now if I do that, I'm going to subtract. I'm going to plug my 0 in. That will be 0 minus or plus, again, 12 cosine of 0. So we got to think of our cosine of 0. Cosine of 0 is 1. So this is going to be 12 times 1, which is just 12. So when I take my value of 144 and divide it by 2, I get 72 plus my cosine of 12 cosine of 12 minus 12. So that will be 60 plus 12 cosine of 12. And that's it. So we can do our decimal if we want to put this in our calculator. We would get approximately 70.1262. All right. Example 5, I have from 1 to 9. And here I have 2t squared minus t squared, square root of t, minus 1, all over t squared dt. Now I want to simplify this before I integrate it. So everything's over t squared, so that just becomes 2 plus. Now remember, this is the square root of t, and this is t squared in the front. So that would mean t squared and t to the 1/2. So this is 4 halves when you look at t squared. So this is actually t to the 5 halves over t squared. So that means I'm subtracting these two, and when I subtract these two, I'm actually can reduce my t squareds, and that will just leave me with t to the 1/2. And then finally minus t to the -2. So this is what it looks like when I simplify it, making it easier to integrate. And this is still dt. All right, so now I'm going to take my antiderivative, and I'll have 2t plus, here I'm going to add 1 over 1, so it would be t to the 3 halves over 3 halves, minus, add 1, t to the -1 over -1. When I simplify that, I will have 2t plus 2/3 t to the 3 halves plus 1 over t, or we can just leave it t to the -1 for now. Okay, now I'm going to evaluate this from 1 to 9. When I evaluate this from 1 to 9, I will plug 1 in and have 2 plus, plug 1 in here, 2/3 plus, plug 1 in here, it'd just be 1 over t, 1. Oh, and we need to do that second part. So I'm jumping ahead. Let's do the 9 first. So 2 times 9 plus, I have 2/3. Now, if I'm going to take 3 halves of 9, that's going to be 9 times 3, which is 27, plus 1/9. Okay. All right, now I'm going to subtract my value of 1 that I just did before, so that would just be 2 plus 2/3 plus 1. Okay, when I simplify this mess, I will get 32 4/9. And that is my area under the curve from 1 to 9 of that function. Okay, there's example 5. Let's see where we're at now. Now we're going to take a look at where this is used as far as applications. So let's talk about that. They give you some good examples here. If you take the integral of rate of change, you get net change. Okay, so what does that mean? So if I might have a volume of water in a reservoir at a certain time, then its derivative would be v prime of t, the rate at which the water flows into the reservoir at time t. So here, if I have that rate from the first initial time to the second time, I will then integrate it and get v of t sub 2 minus v of t sub 1. So this helps me find that value. Let's look at the concentration of a product chemical at reaction time, and you'll see a lot of this is at time. The derivative of this would be, whenever I differentiate whatever this function is, I'm going to take a look at it at the integral of t sub 2 minus the integral of t sub 1. I can also use it for mass measured from the left point of x, and then we have a linear density, and if we take that linear density, once I integrate it and I have my boundary from a to b, I will then substitute in and have my m of b minus my m of a, and that's the mass of a segment of a rod that lies between a and b. So I can find that mass. Rate of growth. Now this is something that we took a look at before we started the calc class. I sent you a video and I asked you to watch it about the coronavirus and how they used mathematical properties to determine the growth of the virus. So if you have the rate of growth of a population, then the net change in population during the time of T1 to T2. So that means the population would increase when births happen and decrease when deaths occur. So the net change takes into account both the births and the deaths. Okay? We can also use it in economics when we have cost functions of producing X units of a commodity. Marginal cost is given by the derivative. So if I integrate it, I then can have c of x sub 2 minus c of x sub 1, which is the increase in cost, and when production is increased from x1 units to x2 units. What about an object moving along a straight line with a position function, st? When you have the velocity, you can integrate to get your position function, and you can look at the area that it's in when you're going from T1 to T2, so an initial time to a second time. So you can see that there's a whole lot of applications here with integration, just as when there were applications with the derivatives. Okay, we'll take a look at example 6. Example 6, we'll do one of these application problems, and I'm on page 325. Here we have a particle moving along a line so that the velocity at time t is this. So we're given velocity, v of t will equal t squared minus t minus 6. And we're saying it's measured in meters per second. And we're going to find the displacement of the particle during the time where t is between and equal to 1 and less than or equal to 4. And we're talking about seconds. Find the distance traveled among this time period. So we're looking for the displacement, we need to find our position function and put our value of 4 in, and then subtract our value of 1. That will give us that length. So how do I do that? I do that by integrating from 1 to 4 of this function. And this is dt. All right, when I do that, I can use the antiderivative. So I have t cubed over 3 minus t squared over 2 minus 6t. I'm going to plug these values in. And once I plug these values in, cube it, square it, multiply it by 6, and then subtract the same. When I plug 1 in, I will get the value of negative 9 over 2, and you can check that in your calculator. So that means the particle has moved 4.5 meters to the left. So this negative tells me direction is to the left. Okay. All right. Now, part B says find the displacement of the particle during this time. So if I'm going to take a look at the displacement, then I want to figure out where my value is positive and where my value is negative. So I'm going to take a look at the absolute value of this function. So if I'm looking at the absolute value of 1 to 4 of integrating, then what I have to do is take a look at first from 1 to 3, because that will give me my negative value. So I need to take my negative of my velocity function, and then I'm going to add from that 3 to 4, as that's where my value is positive. Oh, I don't want to do that yet. We'll do dt. Okay. All right. So I'm doing two separate integrals here. And again, this is dt. There I go with my notation again. Okay, so I'm going to do two separate integrals here. I'm going to look at from 1 to 3. And this is the negative velocity function. So I have negative t squared plus t minus 6 when I take my negative values through. Oh, plus 6 because it was minus. Okay, and I'm going to do that to dt, and then I'm going to do my 3 to 4 of my function where it's positive. And this is going to give me my absolute value distance, not just whether it's moved to the left or the right. So that gives me my displacement. And when I do this and integrate, I will again have negative t cubed over 3 plus t squared over 2 plus 6t, and then over here plus t cubed over 3 minus t squared over 2 minus 6t. And this one I'm going to evaluate from 1 to 3, and then this one I'm going to evaluate from 3 to 4, and then add those together. All right, so once I do that and plug everything in, this minus this, this minus this, I will find that my value is 61 over 6, which is 10.17 meters. So that is the displacement of the particle during that time, how it's displaced. And then finally, the distance traveled, actually distance traveled completely during that time would be the 10.17 meters, okay? All right, so this is direction to the left, part A, and this is total travel, part B. Alrighty, and that is about it. So section 4.4 is now finished, and we will meet again for section 4.5. Have a great day.